Okay. All right. Welcome, everyone. I hope you had a good coffee break. We're happy to have now as our topical seminar speaker, Professor Oleg Ruchayskiy from the Niels Bohr Institute, and he's going to talk about particle physics and cosmology. So, Oleg, please take it away.
Yes, thank you guys for the invitation and for organizing the school. Neutrinos are a hot topic, and it's always interesting to speak about this. And the goal of my talk is to give you an idea how research in neutrinos interesting by itself and carrying a lot of promises and questions and potential discoveries, how this research can advance our big picture. Not only advance, but maybe even consolidate the big pieces of puzzle that we are facing right now. And that's what I mean by keys as a unified theory of particle physics and cosmology. So to start with, particle physics. So particle physics is the enormously successful theory which took humankind more than 100 years to develop, from the end of the 19th century to the dawn of the 21st century. And the beautiful story about the particle physics is that it's a long chain of accidental discoveries, model building, predictions, verifications, and so on and so forth. So the theory was developing gradually, growing, and to demonstrate its success, I like to show the following plot, which is called sometimes Stairway to Heaven. And for those of you who are not familiar with it, what's here? It's a report of one of the LHC experiments, Atlas in this case, which reports measurements in various channels, so different particles, different types of interactions along the x-axis. It's not an axis, it's just beams, if you wish. Just each one is independent. Versus the rarity or frequency of this interaction. And you can see that we predict processes which differ in interaction strengths by 14 orders of magnitude. That's what this axis is. And the beauty of this plot is that there is a gray theory and colored experiment done with various regimes of a Large Hadron Collider. And the beauty is that you cannot see the theory behind the experiment. They are overlap. So across 14 orders of magnitude, you can make very precise predictions and confirm them. And that's what we mean when we say the standard model is a beautiful theory which passed an enormous amount of tests. As beautiful as it is, people always wanted to go beyond, and so they spent enormous amount of human power and electricity to search for new processes which are beyond standard model. And so far they have found nothing at colliders which would contradict the standard model, which means that dozens of ideas and theories, a generation of scientists' works have been buried, of course, with all the honor that they deserve. But the question is now, given how beautiful standard model works and given the absence of any signal away from standard model, is there anything at all? Or the particle physics in its present form is a complete theory? So, to answer this question, neutrinos come and help. How neutrinos come? Neutrinos, as we know since 50s, when the parity evaluation was discovered, are such particles that only their left chiral component interacts weakly, and that's why only their left chiral component is a part of a standard model. That's unlike any other fermion, be it quark or lepton, where you have both left and right chiral components, which combined together give you a mass. Having only left chiral component, the only state which interacts, the neutrino is necessarily massless. That was the state of the art when the standard model was written down in its present form in the 60s. And it was like that until people understood that neutrinos oscillate. There are three types of neutrinos, and they change flavor as they propagate. I will not speak about this. You had several lectures about this, a very good one, just the latest one just finished. So the only thing I want to say is the fact that neutrinos oscillate means that the state which interacts and the state which propagates is not the same state. And this automatically means that neutrino have mass. So the fact of oscillation implies mass. And at this moment, you have to say, okay, so this is a signal beyond the standard model. We should do something with the standard model to explain masses and oscillations. The idea seems to be very simple. If mass requires presence of left and right chirality, let's add the right chirality to the standard model. Now, explaining the mass of neutrinos becomes as trivial as doing it for any other fermion. The question is the following. Does this assumption bear any non-trivial consequences beyond just a simple mass term? As it turns out, it does. Now, right chiral components of neutrinos were not added to standard model because they carry no standard model charges. They're neutral. They don't interact strongly, of course, because they're leptons. But on top of that, they don't carry weak charges. They don't carry weak charges, unlike other right chiral components for electron, muon, or quark. And this means that for them, and only for them, for the right chiral component of a neutrino, its own mass term can be written, known as a Majorana mass term, which couples particle to itself, not to its antiparticle. Now, it can be written, and if in somewhat philosophical rather than scientific sense, we will think about so-called totalitarian principle, which is everything not forbidden is compulsory in the quantum world, then it's not only can be added, but must be added. What does it mean? It immediately means that in your neutrino, left chiral component and right chiral component behave as two different particles with different masses. And this fact has already a quite non-trivial consequences. So, owing to the fact that the right chiral components have no charges, they are often called sterile neutrinos. Owing to the fact that they may have mass, or the corresponding mass eigenstates exist and can be heavy, they are called heavy neutral leptons or heavy Majorana neutrinos. Or gauge singlet neutrinos or right-handed neutrinos. There are many names that are adopted by different communities in different years. But the fact is that adding the right chiral parts to the standard model Lagrangian immediately brings to you new particle or new particles. These particles allow you to explain, first of all, neutrino masses, and moreover, explain to you why left-handed neutrinos, or active neutrinos as we would call them, making distinction between charge eigenstate and mass eigenstate, why these particles are light. Essentially, the idea is that the neutrino masses that we sense is the left-right interaction, the usual standard model-like Dirac mass squared, divided by the right-handed Majorana unique mass. And these two mass scales can be vastly different, and their ratio can be much smaller than 1, and that's why the observed neutrino masses are much smaller than the masses of other particles or masses of right-handed neutrinos in this case. That's how seesaw, that's why the mechanism is called seesaw mechanism, because that's kind of heavy versus light, one putting another up in the air. In a very simplistic way, how do neutrinos get mass? Left chiral component, massless, has a probability to become a right chiral component, massive. Travel for some time, and then with similar probability convert back to the left chiral component. So if you look overall propagation story of the left chiral component created here and detected here, it looks like it traveled through the distance with a speed which was not always equal to speed 4. But owing to the massiveness of the right chiral component was smaller. That's why it looks like a mass for this component, albeit a small one given the probability of conversion. In the same way, neutrino oscillations work. This time, the left chiral component has a probability to become a right chiral component, which then have a probability to mix not only with this flavor, but also with another flavor. So the interaction between right and left is necessarily non-diagonal on the flavor basis. And that's why you created electron neutrino and you detected muon neutrino with some probability. It's all driven by the same model. And running very quickly along the list of most of those questions, if I make such model, can I explain all observed neutrino masses, whatever they will be, whatever we will measure them one day, and all the oscillation phenomena, all the types of the mixing angles, possible CP phase, two types of ordering, everything you've learned in the school? The answer is yes. Given enough right-handed neutrinos, you can explain any pattern of masses and mixing that we can observe. How many sterile neutrinos should there be? 1, 2, 3? Well, the answer is that they don't have to be 3, but 3 is a good number. Also, 2 is possible and sufficient to explain, again, neutrino phenomenology. Are the sterile neutrinos useful for something else? Because that's always a desirable feature, right? You try to follow the calm razor, you try not to introduce new particle for every new phenomenon. You try to make one assumption, right? Chiral components exist and are massive, and draw many consequences. The answer is yes. The rest of the talk is about what the sterile neutrinos can be good for. Is the mechanism which I just showed to you the only way to introduce sterile neutrinos into the game, or introduce masses for neutrinos? No, there are many, many models. The model I'm talking about is the simplest framework, the least number of particles, the least number of parameters. And it just gives you an idea how the portal to new physics can open through neutrinos. But keep in mind that this is not a unique model, so probably the simplest. And finally, do we know the mass? If they have their own mass, this yellow right-hand component, do we know their mass? Can we predict it based on neutrino oscillation data? And the answer is unfortunately no. And this becomes a realm of theoretical prejudice or bias or taste, if you wish. The masses of right-handed neutrinos can be from very small ones all the way down to subelectric scale to the huge ones. And depending on where you are, the sterile neutrinos can be good for various things. And just to guide your eye, so they can be as light as electron, as light as proton, as Higgs, as heavy as we never saw, 100 TeV, 1000 TeV, million TeV. In all these cases, the neutrino oscillation phenomenology will be explained. But on top of that, other kinds of physics emerges, depending on which range of masses you choose or how many particles you choose. Let me guide you a little bit through possibilities. So, particle physics, neutrinos. Let's move now to the universe, to the cosmology. The universe is also, in a sense, a particle physics, and I quote here Yakov Zeldovich, who said that the universe is a poor man's accelerator, meaning that it can give you energies and scales which have never been attained on Earth. And all the particle physics, well, actually all the physics that we know and deduced from our Earth-based experiments have found its way into the model of cosmology. And that's the beauty of cosmological model, that it's kind of unification, a culmination of everything we know about the physics. And that's the most daring extrapolation, I would say, because never have our instruments, satellites, whatever, left solar system. Well, recently they did leave solar system, but as much as that. And yet we dare to extrapolate things to the whole universe. We say that the law of physics, as we observe in this tiny region of space, which is Earth, are the same all over the universe, across all the timescales. And all this physics works because when you put it into the universe, you draw predictions, which you then beautifully confirm. And this is how this theory of hot Big Bang plus inflation, how this whole story emerges, arises, and that's why we speak about precision cosmology, about the standard cosmological models, and can predict things with % precision and measure them. But there are several phenomena in this cosmological picture which do not fit between what we observe and what particle physics tells us. One of those phenomena is the matter-antimatter asymmetry. The fact is that although we observe antimatter in cosmic rays coming from space, and this is how antimatter was discovered in the first place, This whole antimatter is secondary, meaning that it looks like it all has been produced in interactions of matter with each other and with interstellar environment. So, to make a long story short, it seems that there is no primordial antimatter, which, if you put it back into this picture of the hot Big Bang theory, is quite surprising. Once upon a time, there used to be a soup of particles and antiparticles. And at first approximation, there should have been an equal amount of those. But when the time went by and the universe cooled, the soup annihilated. And when it has annihilated, it turned out that there was an excess of particles over antiparticles. So along with the cosmic microwave background, you get some matter. In a perfectly antimatter symmetric universe, you would not get anything but the cosmic microwave background and cosmic neutrino background. That would be all you've got. But given that they exist, something broke the symmetry. And there is no standard model explanation for this. But as soon as sterile neutrinos appear, story changes. Let me give you a cartoonish idea how it works. In the early universe, if there are two sterile neutrinos with slightly different masses, sterile neutrinos can also oscillate into each other, similarly to the way active neutrinos oscillate into them. But the process which takes neutrino of one flavor into sterile neutrino, into another sterile neutrino, and into neutrino of another flavor, has not the same probability as the same process for the antiparticles. So, or to make a long story short, there is a CP violation in the sterile sector. And this CP violation can be enough to explain the difference between matter and antimatter asymmetry of the universe. And it works across many mass scales of heavy neutral atoms, from hundreds of MeV to TeV, tens of TeV, and going all the way up. So, and accidentally, the same particles which explain to you neutrino oscillations can also explain to you baryon symmetry of the universe. And in both cases, 2 is enough, and 3 is sufficient. And that's the beauty of sterile neutrinos as a story. And that's not it. Along with the fact that there is matter and not a primordial antimatter in the universe, there is also dark matter. Namely, that we observe from tracers much more gravity than we can explain by counting all the luminous matter. And this mismatch exists on all scales, from smallest galaxies to the biggest clusters of galaxies to the universe as a whole. The whole expansion of the universe cannot be driven by matter only, given what we know about observables. This phenomenon is known as dark matter. This mismatch between mass you can deduce through gravity and mass you can deduce through other interactions. And I'm not going into details because I'm sure each of you have heard about this or saw at least some explanations. The fact is that there are many observations, not an experiment. There are classes of observations. There is consistency within each class, and there are consistencies between classes. Now, important thing for us is that if dark matter is made of particles, this is not part of the standard model of particles. So whatever its particle is a new particle, meaning that this 17 ones is not everything, and there is somebody else. Or maybe not even one particle, but many particles. Now, sterile neutrinos, can they help? Actually, sterile neutrinos can help beautifully because they are like neutrinos, massive, neutral, long-lived, but they're sterile, meaning that they interact in weaker than neutrinos. From the point of view of dark matter, neutrinos interact too strongly, too intensely. They couple to primordial plasma for too long time. So you need to tune down the interaction of neutrino-like particle to make it dark matter. And sterile neutrino does precisely this. And that's why sterile neutrino is a perfect dark matter candidate. So yes, sterile neutrinos can be dark matter. Can the same particle explain neutrino oscillation and be dark matter? No. Again, based on the interaction strength, lifetime, etc. But given that you have several sterile neutrinos, one of them can be dark matter and contribute only subdominantly to neutrino oscillations, while others do the job. Now, you may ask, Is this a new idea? Is it new, exciting, just developed? Well, actually, the story goes back to 60s and 70s. And since 80s, people knew that sterile neutrinos could not only explain neutrino oscillations, but also generate matter-antimatter asymmetry. And in 90s, they understood that it can explain the dark matter. And these were kind of independent pieces of work, and then people tried to glue it together. And around 2005, the first unified story, I would say, emerged, in which standard model augmented with sterile neutrinos would have such a choice of masses and interactions that it would explain neutrino oscillations, matter-antimatter asymmetry of the universe, dark matter of the universe, and be consistent with every other accelerator observations that I was talking about. So the stairway to heaven would not change a bit. And that's what I call an example of a unified theory of particle physics and cosmology. Now, any theory, no matter how beautiful it is, should have testable predictions. Otherwise, it's just a mathematical game of mind. Can sterile neutrinos be discovered? Yes. There are many ways to discover sterile neutrinos, many experiments, starting from the Large Hadron Collider, going to the future huge scale colliders, many satellite experiments in CERN, experiments like Katrine, about which you heard in the previous talks. All of them can discover sterile neutrinos of different masses with different interaction strengths, but all of them can. And some of those particles, when discovered, will be able to explain to you data on, and confronted with data of neutrino oscillations, can answer the question, are there the same particles which could explain matter-antimatter asymmetry of the universe, for example. Now, sterile neutrino playing the role of dark matter can be discovered in the sky. And in principle, the data which points to it is very complicated, and there is no consensus here. However, I should mention that both the structure formation data known as the Lyman alpha forest and the X-ray data, where you search directly for the decay line of such sterile neutrino dark matter, they all point to the existence of such particle with consistent properties. There are a lot of assumptions which go there. There is no consensus because there are many unknowns and people have different prejudices about what these unknowns can or cannot be. And I don't want to go into the details because this is really taking us outside the scope. Of course, if one of the signals would be confirmed, if you would see that dark matter is actually warm, as sterile neutrino is predicted to be, and that it's decaying, then the whole game would be changing drastically. From a model of particle physics and cosmology would become the model. But what I'm trying to tell you here is the fact that even very elusive particles, think about this, is a particle which interacts weaker than neutrino. Even a very elusive particle can be probed and detected, which kind of slowly brings me to the conclusion part of the story. So for those of you who want to think about this, the first questions, which are easy to answer, means that you should, like, within a couple of hours, get yourself an answer. Try to answer yourself, how many of such sterile neutrinos can be added to the standard model? I was making a cartoon with 3, but it's actually not necessarily. You can easily convince yourself that you can get smaller than 3 or more than 3, and that's perfectly consistent with all the standard model principles. How many parameters do you add to the model when you have sterile neutrinos? 1, 2, 3, 5,000. How many numbers do you have to determine, to fix, to measure eventually, if this is to be a correct model? And how many of those parameters will be fixed by neutrino oscillation data? The data which we know now, or the data which we will know in the future when CP violations will be measured, and mass hierarchy, and same neutrinos double beta decay, all the things which you heard about. It's an interesting mind exercise. What, when, if we measure this, what does it give us? Now, the last question, which is maybe not a question, but a thing to read or to Google, is the model which I showed the only model of sterile neutrinos, or are there others? The answer is yes, there are many others. Sterile neutrinos appear in many disguises. And again, what I showed you is probably the simplest model. So in the interest of time, let me do the summary, which is, in my case, is extremely simple. Taking standard model, successful as it is, adding to it neutrino oscillation, and adding to it the cosmic pi, this all adds up nicely and fits snugly into this model, which can very easily become the next standard model of particle physics. And you can be a part of its creation. Thank you.
Thank you very much, Oleg, for this review. You touch on a lot of aspects of sterile neutrinos. Really appreciate it. Do we have any questions from the audience? You can either write it or just raise your hand. I think Marcus has one.
Yeah, Oleg, very nice summary. I have a question on so on one of your slides 19. I think it's the last one before you start of dark matter. Can you can you walk me through this plot? So the parameter space which is allowed, is that the one which is not constrained by the blue region?
So yes, so this was very schematic, so let me focus on it. What you see here is the mass of sterile neutrino. And this is a dimensionless interaction strength, which shows you by how many orders of magnitude its interaction is weaker than weak interaction. So take weak coupling constant and divide it by million or billion, and that will be your interaction strength. Now, if interaction strength is too high, so blue regions are excluded. The lower line comes from the fact that if all your interaction is below this line for a given mass, you cannot explain neutrino oscillation data. You give neutrinos too small masses. Going above is allowed from the point of view of neutrino masses as high as you want. This tiny angle actually comes not from neutrino masses, because neutrino mass will be a straight line here, but from the predictions of the primordial nucleosynthesis. It gets spoiled by sterile neutrinos because in this corner of parameter space, they survive exactly until the neutrino decoupling. They change number of degrees of freedom, so they change the helium abundance. Now, what you see here is a more interesting story. In principle, there used to be two completely different scenarios of leptogenesis, of baryogenesis with neutrino oscillations. One going through oscillations, and it was ending about 80 GeV, and another one, the resonant leptogenesis. And people used to think that these are completely different pictures. And this recent work of this year demonstrated that actually it can be unified, and that there is a common framework in which you can travel the parameter space from hundreds of MeV all the way to tens of TeV. So everywhere inside between these lines, very important, you can pick up a model of sterile neutrinos, which will explain neutrino oscillation and give you the correct matter-antimatter symmetry of the universe. The green color coding shows you that you first of all should have two neutrinos. That's always sterile neutrinos. That's always the case. It shows you how degenerate they are. So delta m over m is order 1, 10%, 1%, 1 per million.
This is the delta m of the
sterile neutrinos. There should be two of them. As I said, they should oscillate, and both for the resonant leptogenesis and for leptogenesis for oscillations, they should oscillate into each other.
Okay.
Because this serves as an enhancement factor compared to their small Yukawas, which otherwise would really suppress the generated baryon symmetry by orders of magnitude.
Thank you.
We have a question by Tanya Kosinets. I'm going to read it to you, Oleg. Yes. Are all of the seesaw models you listed on slide 26 equally feasible or likely? For instance, the ones from the 1980s, are they still in the game, or have they been deprecated given experimental constraints or so?
Yes, they're still in the game. The fact that they're from 1980s, well, this model is from 1970s, so it's even older, right? The fact that they're from 1980s just means that they were introduced at that time. And these models have more particles, wider parameter space, so constraining them is essentially more difficult, if I may say so. They all, being seesaw models, I mean, those of them are seesaw models, they all share the property of not fixing the scale of sterile neutrinos. That's what seesaw is. You compensate widen scale by another scale, and only the ratio gives you the mass. There are constraints, and these constraints get tight over time, and people work on it, but no. The models which are listed here are viable models, I'm sure, and this is actually not even everything. There are much more.
I see. Thank you. We have and Tanya says thank you. Another question by Dominic Ellert. He says maybe I missed it, but what about decaying sterile neutrinos? I read about them some time ago, but I'm wondering what are the advantages and disadvantages, and what is the current status in that regard?
Okay, so the KV sterile neutrino is an interesting particle because it can naturally, although I don't like this word, explain a dark matter. Fermionic dark matter should be heavier than about half of a keV, and no matter what kind of fermion it is. And you can, so sterile neutrinos of any mass above this can be dark matter if you sufficiently tune their parameters, and that's probably, the keV neutrinos are probably the closest candidates here. They appear naturally in the unified model which I talked about. Being warm dark matter, they may alleviate certain tensions in the structure formation and may actually be preferred by the data. This is, as I said, this debatable question. And what you see on this slide and what you can see in this review is more or less a story of sterile neutrinos, of what they're good for, how they're constrained, what they predict, and how they are limited. And the last thing that I want to mention, and again, I think it was in one of the previous talks by Joachim, that KV scale signal consistent with the coming from sterile neutrino dark matter have been claimed 7 years ago, disproved a number of times, and stays in this uncertain state until the next generation of X-ray satellites will fly to space. So that's the status.
Right. So just to continue maybe on that, the plot you're showing on the bottom left,
yes.
That's motivated by the 3.7
kV line
kV,
or 7 kV.
The 3.5 kV line, right?
So you can see you maybe can see it's the mass in the kV, so it's between 6.6 and 7.4. So that's a 7 kV.
And there is, as far as I remember, there's no consensus on whether this line is real or not, and there's contradicting observations. Am I correct?
Because the line is sufficiently weak, so you need a lot of data to pick it up, and you start to push this data into the realm where you do not. There is no definite procedure how to deal with such enormous, such a high statistical power of data. Because you have an instrument, this instrument is in space. It has a well-known set systematics when you're speaking about percent level precision. But if you want to go to the sub-percent level, you start to dare, you kind of push the instrument, not the instrument, but the data analysis beyond its natural limits. So there is some bias. It's not science anymore, it's art, if I may say so. How to fit data is not a science anymore, as surprising as it sounds. And then there are people who claim that they do the analysis and they rule out everything, and their analysis is very complicated, and then you come and show that you see a 7 sigma line in the data. The 7 sigma line is a line that you see by naked eye. And how these two facts reconcile is not clear.
Right, thank you. So maybe one final question before we break is by Emil Brinch. He's asking, do we have production mechanisms from theory that can explain all the masses from EV scale to TV scale?
For each mass range, there are production mechanisms which can explain it. There is not a unified mechanism which would work across all scales. What's important here in the model like this one all the production happens within this model. So only the parameters which you introduce, or masses of the three particles and their interaction with the left chiral states, are enough to explain the production mechanisms. You don't invoke any other particles. So it's really a standard model plus three particles, plus the standard cosmological picture.
All right. So I think, yeah, I think that answers the question. I don't see any other raised hands. And of course, if there's any more questions, just leave it on Slack and we have the discussion session. Hopefully Oleg can join us later. But for now, let's thank Oleg. Thank you so much, Oleg. It was wonderful. And everybody will break for lunch now, and we come back at 1:30 for more student talks. So thank you very much.
Thank you.
Oleg, nice talk.
Thanks. Bye.
Bye-bye.